so this is chapter 8, I think. Wait. Okay, so after this is Manifest Quadrant. I don't even know. It's been that kind of a day. I don't remember what chapters we're covering. Okay, yeah, chapter 8 is what we have been doing. Because, yeah, so 6 was interpolation, 7 was quadrature, 8 was polynomial approximation, and minimax graph. And now we're at 9, okay? And once we get to 12, we're done. Okay, so now we do, and this is chapter 5 in the notes. So before we're doing polynomial approximation in the infinity norm and the minimax, which can only be figured out in certain cases. And now polynomial approximation in 2 norm is something we can do generally. Okay. Now, that if we're on a certain interval AB, then the 2 norm of a function for an interval is we integrate. This piece of chalk is off. Okay. The absolute value squared times some weight function, and then take the square root of all that. And generally, in a lot of cases, weight function will just be 1, but if there is a different weight function, that'll be made clear from the context. Also, it may seem superfluous to have the absolute value squared, but we need that in case f is complex. Okay. Now, check where I define everything here. All right. Now, when we're talking about the infinity norm, I dealt with normed spaces, so spaces of functions that have a norm like this defined on it, whether it's a 2 norm or infinity norm or some other norm. But we need something more than that for best approximation within the 2 norm. So we need to discuss what are called inner product spaces, which would be a subset, if you will, of norm spaces. Okay. Now, I'm going to recall something from calculus. The dot product. So if you have 2 vectors, u and v, in a vector space like Rn, then u dot v, you just multiply corresponding components and add them all up. Now we're going to do something similar to define what's called an inner product. So a dot product is a special case of an inner product. So now if you have 2 vectors, well, I'm going to call them f and g because we're going to be dealing with mostly functions as vectors, but also by using v sometimes tend to look alike. And I don't want to cause extra confusion. So if f and g are in some general vector space v, so it could be Rn, it could be space of functions, which is what we care about. So an inner product on the vector space V is a function that takes two arguments. So the dots here I'm just using as placeholders. So I'll use the angle brackets to indicate inner product of two vectors f and g. So the domain is the Cartesian product of itself. In other words, you're taking a pair of functions from V and your or a pair of vectors from V and taking your inner product, with the range being the real numbers if we're on a real vector space. Otherwise, the inner product could be complex, but we'll just keep everything real for convenience. And just like the norm had to have certain properties, like the norm had to be non-negative, the norm had to satisfy a triangle inequality, etc. The inner product has properties to satisfy too. So it has to have a linearity. So it's linear in each of its arguments. So if I have an inner product like this, I have a sum in one of these arguments, I can break it up as two inner products with h. I can pull out constants. So C is a constant. I can pull it out like that. Also, as I want to emphasize, C is a real number. Again, the rules are different, things are complex, but I won't get into that. When things are real, the inner product is commutative. Things are not real, but you have to do a complex conjugation. So if you put the second and third rules together, you can pull out a constant on either argument. And finally, the inner product of a function with itself has to be non-negative. Also, inner product of itself is equal to 0 if and only if the vector itself is the zero vector or zero function. So if you have an inner product space, then it's perfectly natural to use this last property to define a norm on a vector space. So it would be the square root of the inner product with itself. And
is that coming off of 2, or is that just another?
Oh, what?
Is that directed? I mean.
Oh, well, it's really inspired by this.
Okay.
Yeah.
Okay.
Yeah. But we wanted to have, the thing is, because it satisfies all of these properties, we could use this, well, okay, so remember a norm has to satisfy certain conditions. And actually, I'm going to go off script here and like to see if I can confirm that it does. So if and this inner product can be any function that satisfies these conditions. Like we don't know anything else about it. So if I go ahead and define a norm this way, the question is this really a norm? Because the norm has 3 properties. The first one is essentially this. It has to be non-negative. It can only be 0 if a vector is 0. So the first property is fine. The second property, if I scale f by a constant, then the norm has to equal the absolute value of a constant times the norm of f. And if I have norm of cf, I can have a c in both of these, and I can pull out both of them. So that property, that second property of norms, what happens if you scale the vector, that's fine. No need to worry about that. The one that's most troublesome is what about the triangle inequality? So I don't know if I've ever checked this out before, so just for fun I'm going to try it. And if I get stuck, oh well. Okay. Now, so what I want is the norm of f plus g to be less than or equal to the norm of f plus the norm of g. So, well, the norm of f plus g, I'll look at it squared, just because so I don't deal with pesky square roots. So now what you can do is that is the inner product of f plus g with itself. Okay. Now, if I use the linearity properties, so property 1 and property 3 together, that would be the same as ff plus fg plus gf plus gg. Now, the two cases where you have an inner product of something of itself, that's the norm squared. So I have norm of f squared plus 2 inner product of f of g, because fg equals gf. And then I have the norm of g squared. Now, I can see from this that it is going to work out, except I need a certain property of these norms that I actually have in mind to prove later. I just haven't got to that point yet. So,
Wouldn't that the inner product of f and g have to be a negative?
well, no, because all right. Hold on, let's see what I have next here. Okay. Here's what I do need. And what I'm going to do is, I'm just going to assume it now and then go back and prove it later. Because I was going to do it anyway. It turns out that this inner product, when it's defined in this manner, satisfies an inequality called the Cauchy-Schwarz inequality.
So it's less than or equal to the 2 times the norm of f times the norm of g?
Yes. So the absolute value of this is less than or equal to product of the norms. So what I can do is, if I go ahead and replace, I can say less than or equal to norm of f squared plus 2 norm of f norm of g plus norm of g squared. And that's a perfect square. Norm of f plus norm of g squared. And now I can take the square root of both sides, and I get exactly that. If a Cauchy-Schwarz inequality is true. Bless you. So, okay. So, for an impromptu thing, didn't work out that badly. But now I need to show this. And actually, this is what I get, especially from this kind of class, where we tend to be more theoretical than other classes, because I enjoy doing this proof, and this is why I can't get to call anybody. So, I know you all don't mind, but still. Okay. So, proof of Cauchy-Schwarz. And it's seen proved in different ways. Let's see, which one do I have? That. Okay. So what I do is, I work with this norm of CF plus G, where C is a constant. Okay. Now, using the same linearity properties as before, so what you see over there, instead of F, you're going to have CF. So that's going to give you C squared norm of F squared plus 2C inner product of F and G plus norm of G squared. Now, because this is a norm of CF plus G, it has to be greater or equal to 0. However, this whole thing can be written as, this is quadratic function in C. Because we have a C squared here, C, and then just like our constant term. When you have a quadratic function that is always greater than or equal to 0, so it can touch the axis and just can't cross it, what does that tell us in terms of like a quadratic formula? So the quadratic, it's behaving either like this, so it
there's no roots or just one root?
yeah. It's one of these two situations. So, in terms of quadratic formula, what does that tell us?
The determinant is either it's either 0 or greater than. No, I don't know. Where am I going?
Oh,
It's something about it's something about
This is what
the b squared minus
right now.
something about
Yeah.
it's real. It's real.
well, things we don't want real roots.
Right. Oh, just kidding. Okay. So it's either 0 or
It's complex.
it's complex.
Which means a discriminant
It's negative.
is negative.
Yeah.
Yeah. Okay, so a discriminant. Here's my unfortunate choice of notation, because you know discriminant b squared minus 4ac less equals 0, except I'm using c up here as a variable. But the point is you have a coefficient of your linear term, so that would be 2 inner product of f and g, that's your b, minus 4a, which is the norm of f squared, and then your constant term, which is the norm of g squared. That has to be less than or equal to 0. But then what happens is, then you just rearrange this, and you cancel the 4's. And then you take the square root of both sides, well, that's gone, and you get the absolute value, and bam, it just pops out. So this is a good technique in general when you have some quantity that you know has to be of one sign, greater equal to 0 or less than equal to 0. And if you can describe it as a quadratic in some variable, but it tells you something about the discriminant. And you can use that to prove it. So I've seen this used in other cases besides this. Okay. All right. Any questions about Cauchy-Schwarz? Well, I've seen it described as like Cauchy-Bunyakovsky-Schwarz or something. I don't know why we're mostly about Bunyakovsky. So I guess if you have a long Russian name, you're kind of out of luck. So, okay. Now, what about function spaces? That's what we need for polynomial approximation in the 2 norm. Okay, I'll make sure I have my function space names right. Okay. Okay. now, so the 2 norm of a function f, and when we're dealing with the minimax case, we assumed f to be continuous. So we're doing continuous functions on an interval ab. But I'm not going to use that space. I'm going to use space L2 of AB. And the way I define that is the space of all functions f for which f squared is integrable on the interval AB. In other words, if the integral exists, it's finite. It doesn't blow up to infinity. So in fact, this allows functions to not be continuous. It could be like piecewise continuous, and that would be perfectly fine. So I define a 2 norm to be the square root of the inner product of f of itself, where the inner product of f and g is just going to be the integral of f times g. So it's kind of like the dot product in a way. A dot product, you multiply corresponding components of a vector and add them all up. Here we have vectors being functions, so we multiply by corresponding x values and then add them all up, where you're adding is really integrating, because what's the integral based on? A Riemann sum. It just has infinitely many terms. So here it is like a natural extension of the dot product, and then we can define the norm in terms of just using the dot product with itself. Okay. All right. Now that we have, and yeah, we're just using this function space because that way we're not roped into f having to be continuous. Okay. Did all that. Okay. Now that I have an inner product space and I have a norm defined on that space, I want to solve the original problem for this chapter. Given a function f in this space, how can we find a polynomial that approximates it accurately? And now we're no longer interested in approximating it in the infinity norm sense. We're not doing minimax. We want to make the 2 norm of the error as small as possible. Okay. So given a function f in L2 of AB, what we want to do is find a polynomial Pn of x, and the subscript, as usual, means as the degree n. That minimizes the 2 norm of the error. All right. Now, the inner product that I just defined, this integral of f times g, I could have put a weight function in there. I'm not going to bother doing it now. I may do that at some other point. But because it doesn't really affect any of the other manipulations, it's just going to sit there and I'll get tired of writing it. So what I'm going to do is, unlike a minimax case, I can actually solve this problem. So I'm going to assume that my polynomial is a linear combination of some chosen basis functions. Okay. So these have to be linearly independent polynomials. So basically, I want these to form a basis for a space of all polynomials of degree up to n. Now, ensuring linear independence is actually easy because if I all I have to do is specify that phi j has degree j, like the exact degree, that will guarantee linear independence. So for instance, I could choose a monomial basis, like phi j equals x to the jth power. So I have 1, x squared, x cubed, and so forth. It's actually not a good choice, but for now we'll just leave it, it could be anything. Okay, so given that these are the unknowns, so how can we find those? So I'm going to substitute this into here. So we want to minimize, and I'm going to have a function that describes my error. And it's going to depend on these coefficients, C0, C1, C2, up to Cn, would be the 2 norm of f minus this sum. And I'm going to minimize the 2 norms squared, just because, again, to not have to deal with pesky square roots. Okay. Now, how do we minimize a function of several variables? Actually, I'm covering that in my upper class, multivariable calculus. I suppose anyone remembers how that's done. How do you find a minimum of a function of several variables? Well, how do you find a minimum of a function of one variable?
You have to take the derivative and set it equals 0?
Yes.
You find your critical points.
And what does a critical point mean in multivariable? What's the difference? Yes. You find where all the partial derivatives are equal to 0. And there's also second derivative tests, but since this is going to be a quadratic function, there's only going to be one critical point that'll turn out to be a minimum. Okay, now to facilitate taking partial derivatives, maybe kind of a pain in this form, but we're going to write this in terms of inner products. So if I write this in terms of inner products, what I'll get is the norm, so using the same kind of expansion as before. So the 2 norm of f squared minus 2 times the sum of Cj inner product of f with Bj plus, and then I'm going to have a double sum, that's a j. Okay, so I'll go I equals 0 to n, j equals 0 to n, Ci, Cj, inner product of f with phi, no, phi with phi j. Yeah, I'll do it. Okay. So I need to take a derivative of this with respect to each of these c's, and then set it equal to 0. Okay, so if I take the derivative of my error function, with respect to CK. Well, this doesn't have any C's in it, so that's going to be 0. Here, this is the linear term. So I'm only going to get something from it when j is equal to k, in which case the derivative of this will be 1. Otherwise, it'll be 0. So I'm going to get minus 2. So the derivative will be delta jk. This is a Kronecker delta. That's equal to 1 if j is equal to k and 0 otherwise. Times inner product of f with bj. And then over to this part, now when I differentiate this, that's going to be a product rule. So I'm going to have ci times the derivative of cj, so that's delta jk, plus c delta ik cj, and then inner product of phi phi j. Okay. So the rule I'm using is the derivative of ci with respect to ck is this delta ik. All right. So if the indices are equal, it's like you're differentiating x, so you get 1. Otherwise, it's like you're differentiating a constant, and you get 0. All right. Now, I want to try to condense this. Hold on, I goofed. This still needs to be a sum. Okay. Now, this is going to be 0 except when j equals k. That means all the terms in the sum will go away except 1. So this whole partial derivative will equal minus 2 inner product of f with phi k. Actually, okay, I know this sounds really stupid, but I'm going to write this as phi k f. Yes, it's commutative. I could write it either way I want, but for reasons that I'll explain later, I'm going to write this way. Over here, if I look at this part, all these terms will drop out unless j is equal to k. So I'm going to get a sum over I, ci, and then j has to equal k. So I get phi phi k. And then for this part, all these terms will go away unless I equals k. So I'm going to get a sum over j of cj phi k phi j. All right. Now, I want to try to condense those two sums into one. First of all, I'm using I over here and j over here. These two sums are separate. There's no reason why I can't use j for both. So I'm just going to rename I to j in here. There's no mingling of i's and j's. So now the two sums look almost the same. Except what? Yes, and why is that not a problem?
Because it has the rules number.
Which rule?
Where the, community.
Yeah, so in fact, I can condense these sums. Okay, and actually I want to have kj. and just indulge my quirks. So we have 2 of those, so now we have a 2. And all the partial derivatives have to be equal to 0. So as a result, what we have is the sum of phi k, phi j times cj must be equal to inner product of phi k with f. Okay, so, and this has to be true for k equals 0, 1, 2, up to n. All right, now, these are called the normal equations. Okay. What we've just done here is
Did that just
we've just solved what's called the least squares problem. It's called least squares because we're trying to minimize a 2 norm. We think of a 2 norm, we're integrating a squared function. It's like minimizing a sum of squares. So, so that's where least squares gets its name. Now, we can actually describe this. This is a system of linear equations, like ax equals b. So this, you can think of as a matrix, A, K, J, that each entry is one of the pairwise inner products of these polynomials with each other. Here are your vector of unknowns, and here is your right-hand side. So this is so you can solve this using techniques for solving linear systems like Gaussian elimination, or in fact, this matrix has a property is symmetric because the inner product is commutative. It is also positive definite because the polynomials involved are linearly independent. And this is really a topic for either 561 or 610, but therefore you could use like the Cholesky decomposition. But in 610 we'll talk about this problem much more extensively from a linear algebra point of view. But the point is, it can be solved. And that's true whatever you use for your phis. You can go ahead and form this matrix and solve it. But the most convenient choice, like using a monomial basis, 1, x squared, and so forth, that would make these really easy to compute. But it turns out that's not a good idea because the matrix that you would get is terribly ill-conditioned. So we're not going to go there. In fact, what we'd like to do is make this system of equations as easy to solve as possible. Okay. The notes I really need are right here. All right, so matrix with these entries very badly conditioned. In fact, the matrix that you would get is closely related to a matrix called the Hilbert matrix. that, where have I written down? Okay. In fact, for these, I can work out these entries exactly. So phi k, phi j is the integral from a to b of x to the k, x to the j, dx. And so just work out the integral. So it's x to the k plus j plus 1 all over k plus j plus 1. From a to b. And then you can go ahead and plug in the limits. So for instance, if a is equal to 0, you would just get b to the k plus j plus 1 over these denominators. These denominators are bad. This is similar to what's known as the Hilbert matrix, where it has these entries 1 over I plus j minus 1. So it's not quite the same, but you have similar issues. And in fact, this matrix is famously known for being terribly conditioned so badly that you used it on their SIAM t-shirts. Okay, you remember that? Yeah, okay. So, all right. Provided a very nice visual. So what we're going to do instead is, where are the books I need? Okay. Instead, we use what are called orthogonal polynomials. Okay. Oh, those of you who have been doing my matrices, multi-quadrant stuff like 685 and so forth, this matrix in general, that's the Graham matrix from that one problem in the Goldman Welsh paper. Okay, so orthogonal polynomials have a property that phi k, phi j, and a product equals 0 if j is not equal to k, and otherwise it's equal to some constant which has to be positive. That's because the inner product can't be negative. Now, if we specify that these are equal to 1, then it's orthonormal. So in that case, then the matrix with entries AJK or AKJ, which is the inner product of phi k and phi j, is a diagonal matrix. And when it comes to solving systems of linear equations, you can't get an easier matrix than that. So what that means is the constants that you want, CK, is just equal to the right-hand side, inner product of phi k with f, over the inner product of phi k with itself, this constant alpha k, for k equals 0 up to n. So, problem solved. Once you have orthogonal polynomials up to degree n. So I have not discussed how we actually get those. That's actually something I have lined up for next time. But what we can see from this is if they're orthonormal, so the inner product of phi k with itself is equal to 1, then CK is just the numerator. So that works out even more conveniently. Okay, but that's just a matter of whether you normalize those polynomials or not. Now, the last thing I want to mention, and yep, I'm calling on somebody. I'll have time to do that now. Is I want to draw a connection. So the relation to this least squares problem where we try to minimize the vector to norm of this system of equations, where in the case where if this system of equations does not have an exact solution, like maybe A is an overdetermined matrix that has more rows than columns, something like that. And the way you solve that problem is to solve, again, the normal equations. So I want to write out the normal equations, in this case, A transpose A x is equal to A transpose B. And if I were to write A in terms of its columns, A1, A2, up to AN, then A transpose A, the kj entry, is AK dot product with AJ. So here it is a dot product as opposed to a more general inner product. But notice it's exactly the same kind of thing. Here we're taking, because you can think of the columns of A as being like your basis functions. They correspond to your fees. In fact, suppose you were only trying to minimize the error not on the whole interval, but at selected points. Then these columns would be the values of your fees at those points. So, so this is like a discrete version of this continuous least squares problem. And your right-hand side, A transpose B, the kth entry, is AK dot product with B. So this corresponds to this right-hand side entry from normal equations for polynomial approximation. If B, each entry is a value of some function f at a certain point xi, like maybe at these points x0, x1, etc. in the interval ab, and aij is equal to your basis function number j evaluated at point xi. So if we're talking about this kind of problem, where the matrix A and the vector B have these interpretations, then AX is equal to your approximation of F that minimizes this sum of squares, f of xi minus this linear combination Cj, Vj of xi. And we take all these errors at individual points and we take the sum of squares of the errors. So this is why we call it a least squares problem. We're minimizing a sum of squares. So in this case, we are only sampling at selected points in AB. But if we take that to its extreme and we want to minimize the error over every point in the whole interval, that's this problem. So the inner product in this case is an ordinary dot product. You take that to infinity, your inner product is an integral over AB. So either way, we have some approach to measuring error and minimizing, and then we can minimize it. Okay. Now, you could use different weight functions to use a different inner product and therefore a different norm. So then your error measure is different, because what you're doing in that case is you're saying that certain parts of the interval AB have more importance than others, based on what has the greater weight. Alright, but I just want to draw this parallel between least squares in the numerical linear algebra sense for those of you who take it next semester. So at this point, what we know is if we have orthogonal polynomials up to degree n, the polynomial approximation in a two-norm problem is very easily solved. What I need to show you, and I will on Wednesday, is how do we come up with orthogonal polynomials for a given inner product defined on a given interval. And some of you know that already from other activities related to KSS, but I figure a review can't hurt. So any questions? All right. Well, we have 20 minutes. So who would like to come to the board and do an interpolation problem?
Is it chapter 6?
Yes, it's chapter 6.
She has 3. And I have 4, whatever that is.
Okay. All right.
Why did you flip a coin?
I don't have a coin. But if someone has a coin, I'll flip it.
Figure rock, paper, scissors. What are we doing? No shampoo. What are we trying to figure out?
Who's going to come to the board?
Oh, good.
Here you go. Why did you raise your hand then?
Because I'm ready to get it over with. It needs to be done.
Okay.
Oh, is everybody done with that?
Well,
I'm
yeah.
sorry.
Is everybody okay?
Oh,
Yeah, go ahead and just use the
Are you
board.
recording this?
Yes.
Oh, Jesus.
Oh. Well, only one person's going to see it.
Okay, cool.
No, I totally watched these.
Oh.
Really? Oh.
I've watched some of them before.
You were watching that when I came in this morning. I saw that.
No, that was, I record him just talking. Just talking to me.
Oh, like only listen to the audio, or?
No, I had the, when we were in your office. I had the,
Oh, that. Okay. Oh, that's different. Okay.
I don't have the question written down, but I mean, I'm just gonna write down general information.
what number is it?
6.4.
Well, actually, depending on how efficient Vivian is, we might come up after all.
Okay. Well, yeah, I'm gonna try to go through it. I mean,
Okay. Yeah. I'm not rushing you at all. Just, we also may have time on Wednesday too.
okay. So this is what we're given in the equation, and we need to show. That is terrible.
I know, but the chalk in this room is just something wrong with it.
Oh wow. Oh, dirty. They have it lined up so it looks like a big piece, but it's not. Okay. So,
Dirty.
yeah. We need to show that n plus 1 over 1 minus 1 over the n is equal to 2 to the n factorial over 2 to the n to the n plus 1 over n factorial. Okay, so the first thing I did was plug in 1 minus 1 over n in for x. And I did this individually because first you have to find x naught and x in using this equation. So then, let's see, for just x minus x naught, I have x naught equals -1, 2 times 0, and then, yeah, I'm sure y'all can figure that out. Okay, so then you would have 1 minus 1 over n minus plus 1. All right, minus the -1, which equals 2 minus 1 over. Okay, so then I just did x minus x1, where x1 equals 2 over n minus 1. Okay, so then 1 minus 1 over n minus 2 to the n minus 1 equals 2 minus 3 to the n. I mean, do you want me to go through basically, so you'll see
Do the last one.
Okay, and then, okay, so x minus x to the n, where xn equals 1. Okay, so then you have 1 minus 1 over the n minus 1, and it equals -1 over n, and then the one before that, x minus x n minus 1 equals 1 over n. Okay, and then this goes on and on. It's like 2 minus 5 over n, 2 minus 7 over n, and so forth. Alright, so adding all of those together, we have, okay, so phi of n plus 1 is equal to 2 minus 1 over n, 2 minus 3 over n, up to, okay, so then I found a common denominator multiplied by everything over n, and then everything was divided by n as well, which becomes n to the n plus 1, because we have n plus 1 n's. I mean, okay, so then this goes to 2n minus 1 times 2n minus 3 up to 1, negative 1, all over n to the n plus 1. Okay, so then I need to do, okay, so if you take this negative 1 out right here, then you're left with 2n factorial, the odd versions, because you're missing 2n minus 2, 2n minus 4, and so forth. So then I rewrote this equation as negative 1 over n to n plus 1, so I can get rid of that part, times 2n factorial, and then divide by all of the even factors. So that's 2 times 4 times all the way up to 2 to the n. Okay. Then, this part right here is the same thing. If you factor the 2 out of every number, you'd have 2 times 1 times 2 times 2, all the way up to 2 times n, which is the same thing as 2 to the n times n factorial. Cool? Okay. So then this equation now becomes negative 2 to the n factorial over, let me write it how they want it, 2 to the n plus 1, because I had to pull it back over from here, and then n factorial. Okay.
Okay.
Cool. Can I erase this now? Or do you want me to just do
Yeah,
it?
go ahead and erase that.
Yes.
Actually, does someone have the textbook on that? Yeah, I want to look at the question, because there's actually something very interesting about this question, which I don't, well, keep going. but
Okay.
I
Erase
don't
this
know
up.
if we bring it up in the book. But in case they don't, then we will discuss how to
Okay.
finish your stuff.
Alright, so then they asked to use Stirling's formula, which is n factorial is equivalent to square root of 2 pi times n to the n plus e to the negative n. Okay, so then we just plug in this for all of our factorials that we have on the other side, which becomes so then these cancel. A lot of stuff ends up canceling actually. So then this right here. I mean, I don't know. Do you want me to do each individual step? I mean, this cancels and this becomes negative n. Okay. And then, alright, so this is equivalent to 2 to the n, to the half, e to the negative n. Okay, and then I combined these terms right here, we have n plus 1 plus n plus 1/2, and then that becomes n to the 2n plus 3/2. Okay, then, I'm gonna erase that, I'm sorry. Okay, so then this part right here, I broke it up into 2 parts where you have 2 to the 2n plus 1/2, and then n to the n to the 2n plus 1/2, so that we can cancel with these n terms. So this is so these two cancel and they leave 1n in the denominator. So then we have negative 2 to the 2n plus 1/2 times e to the negative n over 2n times n. And then we just factor out one of these up here at the top. So then we're left with negative 2 to the n plus 1/2 e to the negative n over n, and then goes to infinity, and that's what they wanted. Boom.
Okay, great. That was fun, wasn't it? Now, I'm going to throw out something else not mentioned in the problem. What on earth does this have to do with polynomial interpolation? Oh, I need to show the rest of your handiwork. Yeah. All right. This expression, where does this come up related to interpolation?
There.
Yes. Okay. These points, how are they distributed? Yes, they're equally spaced points. And look at the endpoints. First one is -1. Last one is 1. So it's equally spaced points between -1 and 1. What do we see about equally spaced points and interpolation? What?
It calls more error.
Yeah, like Runge's example. Now in that case, that was the interval -5 to 5. But what's interesting is, for Runge's example, in that case, n was equal to 10. So I actually took this expression since this is exact, because that one is valid as n gets larger. But and I went ahead and computed this for n equal 10, and what I got was a pretty small number. So so at n equals 10, and it's nice that the iPhone calculator has a factorial button on it. So it's equal to -0.0065, etc. So decently small. However, that's the interval -1 to 1. I would need to multiply this by 5 to the 11th power. Okay, so that's going to be okay. Now, so on the interval -5 to 5, what you get is 319,692. So, ow. So what happens is the error is equal to that product of linear factors, and then you divide by, oh, actually, I divide this by 11 factorial. So let's throw that in here. That makes it nice and small again. But what else do you have in the error? We'll repeat in the error formula. There's this product of linear factors, there's a factorial down below. And what else is in there? Yeah, it's a higher order derivative, n plus first derivative. Okay, so now this is also just the error at a specified point, where it's a point near the right boundary. And I imagine that if we were to do the opposite, instead of 1 minus 1 over n, like minus 1 plus 1 over n, it'd probably be symmetric. Just my hunch. So this is, so if we were to compare this to what happens in the Chebyshev case, the error of the product of these linear factors is bounded by just 1 over 2 to the n. So for n equals 10, okay. Okay, so then this, instead of getting this quantity, we get 0.0000, no, just 3 zeros, 0.000977. So significantly smaller for Chebyshev versus equally spaced. Also, we only evaluated the error of this product at just one point. What happens at other points? That would be interesting to try like a distribution. Like how does this vary over the whole of the interval minus 1 to 1? So that's why this problem's thrown in there. It would have been nice if they mentioned something about it. And actually, even though I've assigned this problem a few times before, it never dawned on me until now why on earth it would do that. I guess because I didn't put this on the test. It's only the homework problem, and I never have time to call on people. So in fact, it's might have been the first time I've had someone do this problem at the board. And while you were doing that, I was looking at expressions like, wait a minute, and it just dawned on me, oh yeah, this is about the error. So, because all I've done before, run these things, say, okay, high degree polynomial interpolation of equally spaced points is bad. And never said anything concrete about it. This problem calls attention to it by highlighting, here's what the portion of the error is like at a particular point near the boundary, and it's near the boundary where we saw the error getting bad. Now this is for minus 1 to 1. So if you have a general interval, like if you take like the radius of that interval, you have to multiply this expression by that to the n plus first power. So depending on how large the interval is, this could get large again, as I showed you here. But then you have a factorial. But then you also have that higher order derivative, and that could get large. So there's all kinds of factors at play, and that's why Chebyshev at least tries to make this part smaller. Can't do anything about the rest, unfortunately. But at least Chebyshev distribution does help. So so sometimes you can figure out something concrete about these things. Like to try to estimate this in general would be kind of a pain, but at least something like this, like a point near the boundary, because of the algebra working out nicely, you can figure something out. All right, and these are kind of things that don't always make it into a class, this is something that someone wants to look into as part of their research, and even if it might be a distraction from the main thrust of things, it's still sometimes things pop out of it that are worth knowing. So just follow your curiosity where it leads. And what's funny is, in a lot of things that were undertaken as research problems long time ago are now like sections in a calculus book, like things like volume by slices, disk method, wash method. Those used to be exercised in the calculus book, and now they're whole sections. That's why calculus books are much bigger than they used to be, much more expensive. Okay, so this is interesting to probably look at. So I'm glad you picked this one. So Brianna, next time. Okay.